Welcome to this lesson on electric fields. We'll explain the concept of electric fields and electric field intensity in an intuitive way. So, what exactly is an electric field? An electric field is a region around a charged object where other charged objects experience a force. This is how charges interact with each other across distances without touching, a concept known as action at a distance. Let's visualize an electric field. Consider a positive charge placed at the center of our screen. The electric field around this charge can be represented by field lines radiating outward from the charge. For a negative charge, the field lines would point inward toward the charge. By convention, electric field lines always point in the direction that a positive test charge would move if placed in the field. Now, let's talk about electric field intensity. Electric field intensity, denoted by E, is defined as the force experienced by a unit positive charge placed at a point in the electric field. Mathematically, it's expressed as E equals F over Q, where F is the force experienced by a charge Q. The SI unit of electric field intensity is Newton per Coulomb, N/C, which is equivalent to volt per meter, V/M. Let's calculate the electric field due to a point charge, according to Coulomb's law. The force between 2-point charges is given by F equals K times Q1 times Q2 divided by R squared. If we consider Q2 as our test charge, then the electric field intensity due to Q1 is E equals K times Q1 divided by R squared. The direction of the electric field is radially outward for a positive charge and radially inward for a negative charge. One important principle in electrostatics is the superposition of electric fields. The principle states that when multiple charges are present, the net electric field at any point is the vector sum of the individual electric fields due to each charge. Mathematically, it's expressed as E net equals E1 plus E2 plus En. Let's visualize this with a simple example of 2-point charges. Let's discuss the properties of electric field lines. First, electric field lines start from positive charges and end at negative charges. Second, the lines never cross each other. If they did, it would mean two different directions of the electric field at the same point, which is impossible. Third, the density of field lines indicates the strength of the electric field. More closely packed lines represent a stronger field. Finally, electric field lines are always perpendicular to the surface of a conductor in electrostatic equilibrium. A special case of the electric field that's worth studying is the electric dipole. An electric dipole consists of two equal but opposite charges separated by a small distance. The electric dipole moment is defined as P equals Q times 2A, where Q is the magnitude of each charge and 2A is the separation between them. The electric field of a dipole has a characteristic pattern. Let's visualize it. Another important concept is the uniform electric field. A uniform electric field has the same magnitude and direction at every point in a given region. The most common example is the field between two parallel plate conductors with opposite charges, far from the edges. The electric field strength between parallel plates is given by E equals sigma divided by epsilon naught, where sigma is the surface charge density and epsilon naught is the permittivity of free space. Let's examine the electric field in and around conductors. Inside a conductor under electrostatic equilibrium, the electric field is zero. If it weren't, free charges would move until the field becomes zero. Outside a conductor, the electric field is perpendicular to the conductor's surface. Near the surface, the electric field is given by E equals sigma divided by epsilon naught, where sigma is the surface charge density. Let's briefly look at some applications of electric fields. One important application is in capacitors, which store electric charge and energy in the electric field between plates. Another application is in cathode ray tubes, where electron beams are accelerated and deflected by electric fields. Electric fields are also crucial in particle accelerators, which use them to accelerate charged particles to high speeds. In daily life, photocopiers and laser printers use electric fields to control the movement of toner particles. Let's summarize what we've learned about electric fields. An electric field is a region around a charged object where electric forces act. The electric field intensity is the force per unit charge and is given by E equals F divided by Q. For a point charge, the electric field is E equals K times Q divided by R squared, pointing radially outward for positive charges and inward for negative charges. Electric fields follow the superposition principle. meaning the net field is the vector sum of individual fields from each charge. Understanding electric fields is fundamental to studying electromagnetism and various technological applications. Thank you for watching.